Let's have a discussion about conversion factors. The conversion factor of interest here is 2 times the number pi times the radius of a circle divided by the number of revolutions over time units. For instance, you might have 3 revolutions per second or 3 revolutions per hour, whatever it is. So this is our conversion factor, where the central angle theta, now this is just a reminder of different things that we're going to discuss. The central angle theta, which is related to angular velocity omega, always has a radius equal to 1 radians. The units are radians, but we don't usually write radians, so I put it in parentheses. And the other thing we want to keep in mind is the arc length of the circle. The arc length S, which is related to the linear velocity v, has a measured radius. So we actually measure the radius and it equals our units. Now, how are we going to use this conversion factor in the cloud? 2 times pi times the radius divided by the number of revolutions per time unit. How are we going to use that? Well, that's what we're going to discuss now. If we have, let's see, revolutions divided by the time units, so revolutions per second, revolutions per hour, whatever, around a circle. So you're given that. You're given the number of revolutions per time unit, and you're asked to find, what are we asked to find? We're asked to find 2 things. Part A, find omega, which is equal to the angular velocity. Now, what is the angular velocity? That's the rate of change of the central angle theta, which has a radius equal to 1 radian. And besides that, they're going to ask us to find part B, v equals the linear velocity. Now, what is linear velocity as opposed to angular velocity? Linear velocity, that's the rate of change of the arc length S, which has a radius of r units. Okay, so here's how we answer those 2 questions, A and B, given the revolutions per time unit around the circle. Part A, we are going to use omega equals the given revolutions per time unit, they actually gave that to us in the question, times a fraction, which is our conversion factor, 2 times pi times 1, where the units for that 1 are radians, which we don't usually write, divided by the number of revolutions per time unit. And that's going to give us our omega. For part B, where they ask us to find the linear velocity, we're going to use this formula. V equals the given revolutions per time unit, now that's what's provided for us, times a conversion factor of 2 times pi times the radius that we have for the circle divided by the number of revolutions over time units. If you look at the examples in the textbook, you'll see that we are using this method to answer these types of questions. The fact is that there's more here. We can use this in other ways, not just what we saw here. If we're given, for instance, the angular velocity omega and the linear velocity, which we call v, and then with that information, we are asked to find the number of revolutions per time unit. The way we would answer this, well, there are 2 ways to do it. If they gave us both the angular velocity and the linear velocity, there's 2 ways. First, part A, using the angular velocity, the thing that they requested, revolutions per time unit, that's going to be equal to a fraction. On the top of the fraction, we are using the given omega, that's the angular velocity, multiplied by the number of revolutions per time unit, and then we divide the entire product over 2 times pi times 1, where 1 is in the invisible units of radians. So that's how you get the answer using omega. Now, if you only know linear velocity v, you can find the requested revolutions per time unit this way. It is it's equal to the given linear velocity v times the number of revolutions divided by the number of time units, and all of that product divided by 2 times pi times the radius, whatever the radius of the circle is, the radius of the entire circle.